Today, we are going on an incredible journey, but we're not going across the globe. We're going down. We're headed deep into the heart of our planet to figure out what makes this world tick, to uncover the massive forces that build mountains, move entire continents, and shape the very ground we walk on.
So have you ever really thought about it? What's going on right now, miles and miles under your feet? Because that solid ground you feel, well, it's really just the thin crust on top of a world that is in constant, sometimes violent motion. Ready? Let's start digging.
Okay, our first stop is right here, on the surface. And if you know how to look, you'll see that our planet's entire history is etched into the landscape around us. Every mountain range, every canyon. It's like a chapter in a story written in stone.
That's the key thing to remember. Nothing is static. The Earth's surface is always in this tug of war. You've got forces that build things up, and then you've got forces like weathering and erosion that are constantly trying to tear them back down. It is a relentless, powerful cycle. And the main characters in this story? They're the rocks.
And this is how they change. It's called the rock cycle, and it's basically a never-ending transformation. It all starts with tiny bits of sediment that get squished together over millions of years to form sedimentary rock. Now, if you take that rock and subject it to some serious heat and pressure deep underground, it morphs into metamorphic rock. And if you turn the heat up even more until it melts completely, well, that molten rock cools and becomes igneous rock. And the whole cycle is ready to start all over again.
So what exactly is sediment? Honestly, the easiest way to think of it is like Earth's dust. You've got wind and rain constantly chipping away at mountains, creating these tiny pieces of rock and dirt. Rivers then carry all that stuff downstream, where it eventually settles at the bottom of lakes and oceans, building up layer after layer. This is the stuff that makes rocks like sandstone and even coal.
All right, now let's go to the other end of the temperature scale. Let's talk about magma. This is superheated, molten rock that you find deep inside the Earth. And here's the key difference you got to remember. As long as it's underground, we call it magma. The second it erupts from a volcano onto the surface, we call it lava. Once that lava cools down, boom, you've got brand new igneous rock. Okay, so we've covered what's happening on the surface, but to really get what drives the rock cycle, and pretty much everything else, we need to go deeper, a lot deeper. It's time to start peeling back the layers of the Earth. The best way to picture the Earth is like a giant onion. On the very outside, you have the super thin, brittle crust. That's where we live. Underneath that is the thick mantle. Then you get to the liquid outer core, and right at the very center, you have the solid inner core.
So why these distinct layers? It all comes down to one simple principle: density. Think about what happens when you mix oil and water in a jar. The less dense oil always floats to the top, right? Well, the early Earth worked the same way. The lightest, least dense materials rose up to form the crust, while the heaviest, densest stuff sank right to the middle to form the core. So let's compare those first two layers. The crust, our home, is basically the brittle, rocky skin of the planet. It's the least dense layer, and it is by far the thinnest. But right below us is the mantle, a super thick, much denser layer of rock that's packed with iron and magnesium. Now, it's technically solid, but as you're about to see, it doesn't exactly sit still. And now we get to the heart of our planet. The outer core is this churning, swirling sea of liquid iron, and all that movement is what generates Earth's magnetic field, which, by the way, protects us from all sorts of nasty solar radiation. But then go even deeper, and you hit the inner core. It's as hot as the surface of the sun. We're talking 10,000 degrees Fahrenheit, but the pressure down there is so immense it actually forces the iron to be a solid. It's literally a solid iron ball at the center of the Earth. This deep interior, the mantle and the core, this is where the real action is. You can think of it as the planet's engine room. It's the source of all the power that drives every major change we see happening up here on the surface.
See, inside the upper part of the mantle, there's a special layer called the asthenosphere. And it's weird. It's not really solid, but it's not really liquid either. It's so incredibly hot that it behaves like a thick, gooey, slow-moving plastic. And it's this sluggish flow that allows the huge tectonic plates floating on top of it to drift around the planet.
So how does it flow? It's all about convection. The easiest way to picture it is a giant pot of boiling water. Hot, less dense rock from deep in the mantle slowly rises. When it gets near the crust, it cools off, gets denser, and sinks back down. This massive, slow-motion churning creates what are called convection currents, and they act like a giant conveyor belt, dragging the plates along for the ride.
And that right there brings us to the whole concept of plate tectonics, because our crust isn't one solid shell. It's actually broken up into a bunch of massive plates that are constantly moving, powered by that engine in the mantle. And this movement is what literally reshapes the face of our world.
And where these plates meet, you get some of the most dramatic events on the planet. When plates collide at convergent boundaries, they crumple up to form huge mountains or create volcanoes. Where they pull apart at divergent boundaries, they create rift valleys and allow new crust to form from below. And where they slide past each other, at transform boundaries, that's what triggers powerful earthquakes.
How do we even know all this is happening? Well, the evidence is pretty much everywhere you look. You've got continents like South America and Africa that fit together like pieces of a puzzle. Scientists find fossils of the exact same species on continents now separated by thousands of miles of ocean. Entire rock formations match up perfectly across those oceans. It's all there, pointing to a past where the continents were once connected.
Okay, so this has been a wild trip down to the core and back. We've seen how continents move and mountains are made. But why does any of this deep Earth science really matter to us, living our lives up here on the surface? Let's bring it all back home.
Just think about this for a second. More than 70% of our planet is covered by oceans. And the actual shape of those huge ocean basins, all the deep trenches and the massive underwater mountain ranges, all of it was carved out and is still being shaped by the movement of these tectonic plates.
When you get right down to it, these geological forces are a real double-edged sword. On one hand, they give us so many things we rely on: valuable minerals, fresh groundwater, and the fossil fuels that have powered modern civilization. But on the other hand, these exact same forces create enormous natural hazards, like volcanic eruptions, devastating earthquakes, and tsunamis. And that really leaves us with a final, pretty big question. We live on a planet that is constantly building itself up and tearing itself down, all at the same time. The story of our future is really going to depend on how well we can understand these incredible forces and how cleverly we can learn to build with our dynamic planet, not against it.